name is Adolfo Castro Campos, and today we'll explain the experiment of the thermal expansion. Any object, when it gets to a higher temperature, it needs to expand. This is because at the atomic level, any object is made of atoms. And these atoms have a specific velocity. This is because this is due to the temperature the object is. If the temperature gets higher, the atoms need to move at higher velocity. So this means you need more space to move. So therefore, the object needs to expand. This can be seen with metals, for example, in a railway. As you can see here, the rails expanded due to heat, and because they have no place to expand, they actually curve themselves right here. So this can be dangerous in certain situations if it is not expected, but we can actually calculate this using this formula, which says the amount, the length of it will expand is equal to a coefficient called the expansion coefficient times the original length times the change in temperature. This is not exact for every object, but for most objects it is correct to a certain value. This includes the metals we're going to use today. So the object of the experiment is to know the coefficient of these three metals: steel, aluminum, and copper. And how we're going to do this is use these three bars and connect it to this apparatus here. First of all, the bars are already prepared with certain holes and gaps in order to connect to the log. And how exactly the experiment is going to work is that, first of all, the bar is going to be connected to a gauge spring arm. This connects to this gauge, which will tell us how much it expands. Because as it expands, it will move the gauge spring arm, and therefore the needle on the gauge will start to turn. Also, we're going to have this here, which can be seen from down here. This is a thermistor, which means that it measures resistance, and the resistance changes with temperature. So therefore, we can calculate temperature using this change of resistance. And finally, on the right, it is connected to this tube right here in yellow. You can see here on the image. This actually creates steam at a very high temperature. We'll pass it through the tube. The tube is also insulated, so no heat escapes. And it's also connected here at the left, so any condensated water can leave and not enter the experiment. So this is set up so that first we calculate the length and the resistance of the bar, and after we pass steam through it, it will heat up, and after everything stabilizes, we will calculate both the resistance and the expanded length. We know it stabilizes as we can calculate the resistance in real time, and when it stops moving around and stabilizes on a certain value, we know that everything is stable. So here were the recordings for the three of them. Copper is in orange, steel is in black, and aluminum is in gray. As you can see, here is the first length. All of them measure 700 millimeters, and each of them measure a different resistance. This is expected due to they are made from different metals and they conduct usually different. So therefore they have a different resistance. This is in kilo ohms. Then here we have the expansion after the heat, after we pass the steam. As you can see here, the aluminum expanded more than the other two metals. And also we have the resistance at the end of the experiment. As you can see, it's very different. It's around 1,000 times less than the original one. Now, from the resistance, we can actually calculate the temperature. Here is a thermistor conversion table. This actually tells us a resistance value and its corresponding temperature in degrees Celsius. How I calculated it is that because this is not a linear relationship between temperature and resistance, we need to use this table. So for example, imagine the value is between 95.4 and 91.1 kilos. How I calculated it was first by subtracting this number from this number. No, we get a negative value, and then let's call this value x. Then we divide by this value of 1 over x, and this is the corresponding change. One change in resistance corresponds to this amount of change in degrees Celsius. So with this, then we multiply by difference of our measured resistance, let's call it omega, and we subtracted the base value, in this case 91.126 kiloohms, and then we multiply this by 1 over x. This tells us the amount of degrees Celsius different from this value here of 27 degrees. We just need to know the range of which it is. In a nutshell, we actually calculated it by taking these two points, the two extremes of where the value sits, and imagining if there is a linear relation between them. So here are the results using this method. We got that for copper, it started at around 25.5 degrees Celsius, for steel was 30.5 degrees Celsius, and for aluminum was 28.5 degrees Celsius. Then here you can see the changes in temperature due to the steam. They got quite a bit hot, and therefore the final change in temperature, which is this 3 right here. Now from this we can use the formula we saw before, and we want to get here the coefficient, which is represented by alpha. So therefore alpha will be equal to the change of length divided by the original length times the change of temperature, which is what we calculated right here. So doing this calculation, we got these values here on the left. They are quite small. These coefficients are quite small. We actually have a list of the expected values, the theoretical values, which remember are times 10 to the minus 6. For copper and aluminum, it's very clear what the values are. But for steel, it's actually a range between 11.3 and 13.5 times 10 to the minus 6, 1 over degrees Celsius. And as you can see here, our experimental value for the coefficient is between that range. So theoretically, we could say that it has a 0 error if we take that the expected value is the same because it is in the range. But instead of saying that, we actually took the error for both of these extremes. So here's the calculation of the errors. Here you can see first the experimental values for the coefficient, the theoretical ones. For steel, as you can see, there are two of them, the two extremes. And here are the errors. As you can see, they are very small, but if we compare them to the theoretical values in percentage, we can see they are really quite small, especially for copper. There's no doubt it was very close to the expected value of 5%. For steel, remember, theoretically you can say there was 0% error because it was between the two possible values, but if we calculate them individually, it's 4%, or at the worst case, 13% of error. And for aluminum, it was a bit higher than copper, for example, but I would say it's still really small, 12%. So therefore, we showed that this experiment was accurate. It approximately gave us the correct values for the coefficient, and we also learned that we can measure expansion and all these changes quite well. Thank you for watching.